Okay, it's 10 o'clock. Let's get started. So thank you everyone who is logged into this call. You are all in muted mode, so don't worry about any noise in the background. We're going to be taking you through advanced FEA, Advanced Finite Element Analysis, with myself and Frankie. But without further ado, let's get started. If you do, during the webinar, if you do have any questions that arise, there is a little questions box. If you could use the questions box to type your questions in there, we will either try and answer them during the webinar, during the presentation, or at the end if we have time. But if we do not have time, we will answer all questions after the webinar. So thank you all for attending. Without further ado, let's get started. So my name is Simon Brand. So I'm the manufacturing sales manager here at Nanomachines. I've been with Nanomachines for 6 years or so, but I've got 16 years experience in the industry, and a lot of that has come in and around the world of simulation, the world of finite element analysis. And today, the main thing we wanted to sort of focus on is a tool that a lot of you already have included in the product design and manufacturing collection, namely Nastran. So Nastran, for its history, I'll let Frankie do the history of Nastran. But essentially, you know, the world of FEA is kind of split into three worlds. There's the FEA side, what we all know as FEA, but there's the fluid dynamics side, and then there's the injection molding side. Obviously, we're talking mainly about the Nastran, the FEA element today. And there are a couple of things that typically customers want to be able to do with finite element analysis. But it's all really to do with the same thing, whether you're making pieces of industrial machinery or whether in the automotive industry. Ultimately, all of our customers are striving to design the best products they possibly can, to sell the most products they possibly can, and ultimately, as a business, wanting to produce greater profits. And that's kind of regardless of which industry you're in, kind of what we're all striving to do. And there's a few things that people want to do with FEA, and some of the things that we're going to be focusing on today. Now, whether that's structural integrity of the product to ensure that the product that you're manufacturing is the best product, whether you want to reduce the number of prototypes you're producing at the front end, whether you want to reduce the amount of material you're using, or whether you want to just make sure the product is the best possible product it can be. But first, let's talk about a little bit about Nanomachines. So some of you know Nanomachines, you know what we're all about, but essentially we're the largest pan-European platinum Autodesk reseller. We're located in multiple countries around Europe. Our head office in the UK is in Tame in Oxfordshire. Most of you will know that. But we focus on a lot of Autodesk products, as you may or may not know, in and around manufacturing, around simulation, and around data management predominantly. But we also, some of you may or may not know, we also develop our own products. We have a number of additional products that do specific tasks around manufacturing, around electrical, around data management. And we've also teamed up with some additional products to do some specific tasks around data management or scanning, perhaps. And these have allowed us to gain multiple accreditations over the years. Can talk to you more about these later, but let's move on to the simulation stuff. So we've at Nanomachines in the UK, we've had multiple successes with various customers, some of which may or may not be on this call. One of which, Ashton Bulk, is one of our customers, and they create large tipper trucks to lift trains upside down to tip coal out. Now, these guys had a particular problem where they were having some failures with some of the gripper arms, and wanted to be able to make sure that they were built in the best possible way with as minimal material as possible. So they used us and our experience with Francisco to be able to analyze the gripper arm to make sure that even when water had gotten into these coal trucks and frozen, and there was even more weight than normal, they were able to still satisfy their requirements for manufacturing. Another one of our customers, Facade Hoists, They make these winches that hang over the side of large glass buildings typically for window cleaning. But they found that some of the large buildings, if one of the panels of glass needed replacing, that they were being used, their winches were being actually used for lifting these huge panels of glass up to be replaced, and actually wanted to prove whether or not they had the structural integrity to do this. And they use Nanomachine to train them and to work alongside them to be able to prove or disprove whether that was possible. Another one of our customers, Aquifer, they make these solar panel, floating solar panel systems that float on the sea, and actually wanted to be able to test whether it could withstand hurricane conditions, and used us to prove or disprove, actually disprove, that this thing would be able to withstand winds of 150 miles an hour, which it couldn't. Without further ado, I'm going to stop talking, and I'm going to hand over to Francisco, and let him continue with the presentation and continue with showing you a bit more about Nastran. Yes, Francisco, are you there?
Hello, thank you, Simon. Hello, everybody. I see a lot of familiar names on the attendees list. I've had the pleasure of training a good many of you, so welcome back, welcome back. I can see you've got an appetite for FEA. For those of you who don't know me, I'm a bit excited on this topic. I enjoy the opportunity to be able to use Nastran. So, yeah, that's me. Hello, my name's Francisco Perez-Smith. People call me Frankie for short because Francisco is way too many syllables. I work as an applications engineer for Nanomachine. My background is in mechanical engineering. I also have an international finance thing, but it doesn't help here. I've been in this business for about 4 years, training people in software and providing consultancy. But I also have 4 years in the design office and 3 years on construction. I love all things CAD, CAM, and K, nuclear fusion, motorcycles. So yeah, motorcycles. All right, so what is Nastran? I'm sure that lots of you know because I can see that you've done my training before. But for anyone that's new, Nastran is a world-class finite element solver, and it's typically used for structural analysis and thermal analysis. It was originally created by NASA in the 1960s. It actually stands for NASA Structural Analysis. And it was used for the design of the space shuttle. I'm just going to minimize this if I can. Maybe, no, it'll do whatever it wants. Wait, there we go. Okay, it was used in the design of the space shuttle and similar vehicles. So yeah, very, very big shoes we step in. So yeah,
Frankie,
today
Frankie, do you want to move the go-to-meeting thing? There, click that button. There you go. Cool. That's better.
Yeah, so today Nastran exists as in part of the product design and manufacturing collection through Autodesk. And it's really exciting because it's, in my opinion, the first time that really, really powerful FEA is available to a wide number of people. Today it exists as an add-in for Autodesk Inventor, which means that you can use Nastran without even having to leave the Inventor environment. It's very exciting. There we go. So why do we bother with Nastran? Doesn't Inventor already come with its own native stress analysis tool? It does. Inventor's FEA tool, stress analysis, it's really good for verifying very simple design problems. It can perform like linear static and modal analysis. So basically it can deal with the very small loads and vibrations, and pretty much only with metals. But you're very limited in how you can input and output. Whether it's Nastran's far superior. You've got more study types, so you can do nonlinear and impacts and fatigue. We'll go into those shortly. More material types, so you can deal with polymers and ceramics. So you're not just limited to metals. And this is really, really important because so many products out there are plastic, and plastics behave entirely different. You've got better case study setup, so you have greater control over how you're defining the problem to the solver. What's allowed to slide, what's allowed to rotate, how do surfaces contact one another, et cetera, et cetera. You got better meshing tools, so you have greater control over the mesh, and you'll see some very, very nice meshes later today. And at the end of the day, you got a better solver, so it's more accurate and more comprehensive results. The post-processing is also nice in that you can query the model for a lot more. We'll have a look at that shortly. So what kind of problems can Nastran solve? Mainly for mechanical problems, you can deal with linear static problems. So, metals at low displacements, nonlinear static, vibration. You can even have time-dependent loads and impacts. And we're going to see how we can use that to calculate plastic deformation later. You can also do things like fatigue calculations, and you can work out things like thermal expansion and heat-induced stress. And it can involve a whole plethora of materials. So it can do like metals, polymers, so plastics, ceramics, but it can also do plies and laminates. So you've got access to carbon fiber and fiberglass, and also anisotropic materials, so 3D printed materials. This is special because 3D printed materials are weak in the axial direction, but very, very strong in the hoop direction. And simulating that properly is a bit of a challenge, but Nastran can handle it. So yeah, specifically what kind of study types can it do? There's quite a few, I've summed them up here. It can do the linear static analysis, which is a quick and easy one that you can do with the Inventor's FEA. But the real price of the ticket comes with nonlinear static analysis. So you can push metals beyond yield, and you can deal with plastics and laminates, and yeah, very exciting. You can do frequency analysis, so you can calculate normal modes and natural frequencies. But you can also calculate how your model is going to respond with respect to input frequencies. So you can specify how the structure is going to damp out the energy, input a frequency, and see how it's going to shake. It can also do buckling calculations, pre-stress, so bolted connections, transient response, so basically you can give it an event where different loads are applied at different times. It can calculate fatigue and thermal. What kind of problems can't it solve? So it will struggle with fluid mechanics problems, plastic molding and electrical problems, and a few others. Things that involve large amounts of dynamic movement. Very recently, Autodesk include explicit analysis, which means that you can do it, but it's typically not built for that kind of problem. Nastran and all FEA packages struggle with natural wood materials. This isn't because the FEA can't handle it, it's just wood materials are complex in their makeup. Things like grain and things like what year and the humidity in which it grew all affects the mechanical qualities of that material. But that said, you can get pretty good approximates for natural wood materials. So before I get started with the practical examples, the question always comes up, linear versus nonlinear static. Why is it a big deal? I like to visualize it using this amazing fishing rod that I've designed. So what would happen if we held a fishing rod and we had a very strong bass pulling it with 1.1 kilonewtons on the end? We'd see a very, very large flex in that rod. Large flex obviously means large strain, which means that the linear analysis won't yield good results anymore. We'll need nonlinear analysis. I'll give you a practical demonstration of what that looks like. So here we see the calculation being performed in a linear static analysis. When we hit play, we can see that we are getting deflection, but it's deflecting strangely. This is because the calculations are performed on a single mesh, which is calculated at the start. But as we can see, as the rod flexes, we will see significant deflection in the material itself, which necessitates remeshing every so often. So we'll rerun the calculation using a nonlinear static analysis, and we get a much more true to life response. It achieves this by remeshing the rod when the deflection becomes significant enough to change the results of the calculation. Now, you might say, oh, that's fantastic. We'll be able to work out the plastic deformation that's going to result once we take off the load. But that's not a nonlinear static, that's a transient problem. So we're going to have a look at that now. This is one of the magic qualities of Nastran. You can calculate plastic deformation. So here we have a scenario. It's a very small lever and it's being overloaded with about 20 kilograms. What we're going to see from the linear static analysis is that the von Mises stress is going to exceed the yield strength, and this will cause plastic deformation. We're also going to see that the deformation is going to be quite large, and with a large deformation, that's going to necessitate a remeshing of the part. So therefore, the problem is very non-linear in nature. So the challenge here will be to calculate the plastic deformation in the lever once we put on the load and take it off. The temptation might be to come along here and do a nonlinear static analysis, But that won't be sufficient because nonlinear static analysis will show us only how much it deforms when the load is fully applied. What we want to see is putting on the load, taking it off, and seeing what will be the resultant plastic deformation. Very, very tricky, but Nastran can do it. So let's have a look at that. So here we've got the amazing lever, and we're going to bring it into the Nastran environment. So we'll come to the top, environments, Nastran. And here we've got the Nastran environment. For those of you that are familiar, we can see that there is a solid idealization already assigned to the part, and a material has been assigned to the part. We'll quickly look at the material properties and see, we can see that the material assigned is mild steel, and we can see the allowable yield strength is 207 megapascals. So we're going to see how this design responds to a load of 200 newtons acting down. I'll draw your attention to the bottom left here, the nonlinear button. If I click it on, we can see that it's not enabled for the moment. We'll keep that in mind. So with that, let's go ahead and put on a very simple load case. I'll fix these two to simulate a stuck shaft. And we're going to put a load of 200 newtons acting down. Now, if you can't see the load, it's always facing away from the surface that you put it on. So we can increase the density and we can see the load there. I'm going to reduce the density, and there we go. Okay, so next we'll come along and we'll do a mesh. So I'll come to mesh settings. I'm happy with an element size of 0.75. Here we go, and generate the mesh. Now, if I was performing this calculation for a proper job, what I do is use a much finer mesh. But because of the nature of nonlinear calculations, the finer the mesh you have, the exponentially more computation time you need. And so for brevity, we're going to be using this potato mesh. So let's go ahead and run the analysis. This is just a linear static for the moment. Now, linear static is very quick to calculate, so it still has its use. Wonderful. Okay, so here we can see a solid von Mises stress of 394 megapascals. Now we might say, okay, yeah, that's a lot. That's a lot more than the yield strength of 207 megapascals. Let's see if we can trust those results. Before we do, we'll come along to displacement, and we'll see we're getting about almost a mil of displacement at the tip there. Now, let's see the safety factor. So we'll come to other, safety factor, and we can see the safety factor, which is calculated as the yield strength over the von Mises stress, is 0.58, which means it's going beyond its yield point. Now, we can already know, yes, this is going to be a nonlinear problem. So let's go ahead and change this to a nonlinear analysis. Very, very simple. We'll come to analysis, edit it, and change it from linear to nonlinear static, and click OK. There's one more very, very important thing that we need to change, and that's we have to come to the material properties, and we have to turn on nonlinear material properties here. So by default, Nastran assumes linearity in the material. That is to say, you double the force, you double the stress, and you'll double the strain on the material. Whereas here we're going to change it to an approximation of a elastoplastic. So this is elastoplastic bilinear. And if you see this little mock-up of the stress strain curve, we can see the stress strain curve, which is linear up until yield, and then is approximated in the hook to be this second straight line. So we've turned on an approximation of nonlinear material properties. While we're in town, I might as well point you to here. We can come to plastic, and if you have all the material data, you can program in the full stress strain curve. But for brevity, we will use this approximation. So here we've got the option of turning on intermediate output results. So I'm going to turn them on. And what that'll allow us to do is see how, what the displacement is going to be with 15% of the load or 50% of the load. Sometimes it helps you understand how your product is changing shape as the load is applied. Now, this will take a little bit of time, so I'll explain what it's doing. Nonlinear static and linear static make the assumption that a load is being applied slowly and consistently to the design. So things like damping aren't involved. Things like plastic deformation can't be calculated, but you will see the maximum displacement that results from this input load. As you can already tell, the nonlinear problems take a bit longer to calculate, and that's because Inventor not only has to remesh it every so often, but it has to rerun the calculation for that new mesh. So you can imagine how long it would take with a very, very fine mesh, you know, with a very, very large part, and this is why we always recommend very powerful computers for this, this kind of calculation. So there we go, wonderful. Here we can see, wonderful, the maximum von Mises stress. So linear static calculated it to be 395 megapascals, and nonlinear static calculated it to be 295 megapascals. So a great deal smaller, but nevertheless still beyond yield. At the top, here we can flick between increments of the load. So let's see the displacement or the stress at 15% of the load. There we can see. But this doesn't tell us what the shape is going to be after we finish. After we take off the load, what is it going to be? So we can do that using what's called a nonlinear transient response here. Now, nonlinear transient response lets us set up an event. We can set up a time, we can put on a load, we can take off the load, and we can even specify, if we wanted to, damping. So how does your structure get rid of energy? Because it takes a long time to calculate, we're going to suppress damping for the moment. But we're going to set up the event. So we're going to start off with here, dynamic setup 1. Here we can set up the duration of the event. So we might say, let's go in time steps of 0.25 and have 8 of them. That means that we have a 2-second event. The second step is to come to your loads. And here we see a new option for a transient table. This allows us to put a multiplier for this load at a given time. So I'll show you what that looks like. We'll click define a new table, load scale factor versus time. And here I'm going to put in some increments of interest. So I'll say 0, 0.5 seconds, 1, 1.5 seconds, and 2. And we'll start off with a load scale factor of 0, go from 0 to 1, and go back down to 0, and end with 0. If I show the XY plot, we can see what that looks like on a graph. So we can see that the load multiplier starts off at 0. Then at half a second, we apply the load up until 1 second. Then we take it off. And then we wait until 2 seconds. So wonderful. I will stop gas bagging and start the calculation because it takes a little bit of time to do that. But the upshot of this is that it allows us to see what happens after the event. So if this doesn't load, if it takes too long, I've got a backup with the results already loaded. In fact, I might do that. Here we've got the same setup. And I'm just going to load my previously finished results. There we have it. So at the top, here we have the option of choosing what time increment we have. So at the peak load, 1 second, we're going to see the same results that we saw in our nonlinear static analysis. We can see that it's 295 megapascals, and the peak displacement is 1.5 millimeters at that tip. However, what happens when we take off the load? We'll come to time 2 seconds, and here we'll see, shock, it hasn't returned to its original shape. The plastic deformation is real. Wonderful. So we can see that we've got a residual displacement of 0.6 mil at the end there, and we'll have a look at the residual stress in the frame by coming back to von Mises stress, solid von Mises stress. And there we have it, 148 megapascals of residual stress in the arm. Now, if you need to produce a report and you have to animate this, here we can come to multi-set animation settings. Say, let's go from 0 to 2 seconds. we'll turn on the axial displacement so you can see the true deformation of this material. And we'll change the mode from full to half. And clicking animate will let us see the event as it happens. So this is particularly useful for people that have to create machines that say, for example, fold sheet metal or bend pipes, or worst case scenario, you're doing an impact analysis and you need to know what's my product going to be like when it after it drops. Up there, just finished the calculation on the other one. So here you can see the animation and it'll just cycle through. Okay, so the load applies, peak displacement, it's released, and there we see the plastic deformation. Amazing, incredible. What a wonderful tool. So I'll go ahead and close that. And we'll move on to the next one. Wonderful. So excellent. So next we'll have a look at an example of fatigue. So what we're going to have is a very simple metal clip, and it's going to be cyclically loaded with 15 newtons. Now, the 15 newtons is going to induce not that much stress. It's going to be about 50% of the yield strength of mild steel. While it's not going to cause plastic deformation, and while it will be a linear problem, it will eventually fail due to fatigue. So what we want to do is calculate the number of cycles to failure. And we're going to use a multi-axial fatigue study. So here we go. We'll come into Nastran. And we'll open up a fatigue study. Here we go. So we're going to set up the load case. In this case, it's very, very simple. We're going to fix these 2 feet. And we're going to act down on this face with 15 newtons. Next, we have to assign a material. So we'll come to solid 1 and assign mild steel. We'll do a very quick linear static analysis just so that we can get a feel for the stress. Say run. And what we can see here is a peak displacement of about 0.015 mil. The clip is tiny. But if we come to stress, we can see a maximum von Mises stress of 100 megapascals. So a good rule of thumb is that the yield limit for mild steel is approximately, I think it's 40% of the ultimate tensile strength. So eventually this will fail. So let's go ahead and change it into a fatigue study. We'll come to analysis 1, change it from linear static to multi-axial fatigue. And it's nearly set up. All we need to do is come into the fatigue setup and set up a duration for the event. We'll say the method is von Mises and the event duration is 1 second. We'll come to the load, and as with the transient, we're going to assign a table which will describe to Nastran how this load is being applied. 0, 0.5 seconds, and 1 second, we will put a multiplier for the load. So we can see that the load is applied, then removed. Now, why bother? It's called multi-axial fatigue because it's in our power to put a second load acting in another direction, and that will be included in the FEA calculation, in the fatigue calculation. Oops, there we go. But for brevity, we're not going to do that. We're just going to put a simple load. Last thing, we'll come to the material, and we'll assign fatigue properties. Now, I've trained this way too many times, so I happen to remember the fatigue properties of mild steel. They are 0.25, so 250, 1000, blank, 0.005, 50. So this is something you get from a material data sheet. For your enrichment, I'll show you at the top, we've got 2 tabs. We've got the stress strain curve and the stress life curve and the strain life curve. If you've got a very large stress, you probably want to use strain life instead of stress life for calculations, but because the stress is quite small, this will suffice. So we'll say OK, and now we can see nonlinear has been turned on. Let's go ahead and run the calculation. Very, very quick. And here we can see the number of cycles to failure. Now, most of the clip isn't very stressed, so it can endure a lot of cycles. But we can see where the peak stress is. We've got the smallest number of cycles. So this fatigue calculation calculated around 440,000 cycles to failure, which may be within its design life, or it may be a terrible failure and we might need to thicken it a bit. But very, very quick and easy to do fatigue studies. So wonderful. Let's move on to the next. We'll finish that and close it down. So next we've got a buckling scenario. So here we've got a tall pole and it's loaded with 5 kilonewtons. Now, you know, if we think about it, okay, if everything's perfectly aligned, the pole should be able to take a 5,000 Newton load. But in reality, what we'd see is a kinking to one side and a buckling failure. So how do we predict that? What we're going to do is calculate how the design responds under 5,000 Newtons load in a linear static analysis. And then we're going to verify whether it's going to buckle or not. We're then going to move on to calculate, okay, exactly how much load can the pole take? So let's have a look at Nastran. We'll come to the buckling. And here we'll set up a very simple scenario. We'll come here and apply a constraint to the bottom to keep it fixed. Apply a load acting down on that face. And we might give it a load of, yeah, so exactly 5,000. Very good. If you can't see it, if you increase the size, there's the arrow. But yeah, so there we've got the load. Next, we can see that mild steel has been applied to it. All we need to do now is generate a mesh. Again, if this is a real calculation, I'd probably use a finer mesh and mesh controls. But for brevity, we're going to run it with this coarse mesh. So here we can go ahead and run the calculation. And the linear static study is going to lie to us dreadfully. If we trusted this study, we'd say, oh, wow, you know, this pole is amazing. What a pole. It can handle the stress very well. We're seeing only 51 megapascals von Mises stress, well below the 200 needed for yield. But reality gets in the way of this nice model, which means it will kink to one side. So how do we calculate that? So what we're going to do is change the linear static study to a linear buckling study. So where are we? Linear buckling. And click OK. And now we're going to come along and run the calculation again. Only take a moment. Linear buckling tends to be pretty quick. And there we have it. Now you might say, Frankie, you've screwed up. Look, the von Mises stress is even smaller than it was. But interestingly, it's kinked to the side like that. We don't care about this stress at the end of the day. What we care about is this value up here. This is the eigenvalue that gets calculated for the stiffness matrix. So what we want to see is that eigenvalue being greater than 1. What the eigenvalue means is its resistance to buckling. Because this eigenvalue is calculated at 0.615, we can predict that this is going to buckle under the 5,000 Newton loads. Thankfully, we did the calculation and we don't have to have the failing pole. Now, wouldn't it be nice to know exactly how much force in that direction can the pole take? Now, you might say, oh, okay, you know, trial and error, and I'll change the load until I get an eigenvalue of 1. But I'll show you a cheat, a much more elegant way of doing it in this simple scenario where we've got 1 load acting on it. We'll come back to our load setup, and this time we'll replace the 5,000 Newton load with 1 Newton acting down, and run the calculation again. And what we're going to find is the eigenvalue. There we go. The eigenvalue, when it loads, what we find now is that the eigenvalue with a 1 Newton load acting down represents the load that the pole actually can take. So this can take about 3,000 newtons, 3,078 newtons acting down before it will yield due to buckling. So linear buckling calculations tend to be pretty quick and easy. The question often comes up, when do we need to consider a nonlinear buckling scenario? A nonlinear buckling scenario is considered when significant deformation in the structure will then yield a buckling mode. So imagine that you're pressing down on this pole and it's structurally sound until it deflects slightly, and then you'll start to get a scenario which is likely to buckle. But those buckling calculations tend to be pretty computationally intensive. So if you can get away with a linear, definitely use linear. Okay, wonderful. The last example that I'd like to show you is a thermal study. So what we'd like to do is have a look at an exhaust system. So here we've got a beautiful exhaust system, and what we want to do is feed it a simple scenario. We want to have a fixed temperature at this end, representing heat from a motor. Maybe it's switched off, who knows? And we want to assign convection, so that is to say heat loss, at these surfaces. So how can we do that? Let's go ahead and come to Environments, Nastran, and this time we're going to run a new kind of study called a linear steady-state heat transfer. So here we're going to go and start off with a load, a constraint on this face, but it's not your typical constraint. Because it's a thermal study, this is going to be a thermal constraint. We're going to say, oh, great machine, no matter what, stay at 450 Kelvin on that face. Next, what we're going to do is assign it convection, so the ability to lose heat. Without the ability to lose heat, eventually the whole thing would just be 450 kilonewtons, 450 Kelvin, and you're not going to get adequate results. So here, we're going to come and assign load, and we're going to come to convection. So this will allow the exhaust to get rid of heat through the magic of convection. So we'll assign the faces that will be convecting away the material. You might assume that the faces near that one are covered in gauze, but there we go. Say it can lose heat through these faces, and we'll say that it's in quite a hot environment, so 322 Kelvin ambient, and the ability to get rid of it is 0.027 convection coefficient. Now, these convection coefficients you usually get from studies, which will say, okay, you know, what is the convection coefficient of mild steel in still air? The problem can arise that you will have significant airflow. So say, for example, you've got a fan blowing over the exhaust, and unfortunately, Nastran can't calculate the airflow and the subsequent effective convection coefficients. If you wanted to do that kind of analysis, you'd have to step it up and get Autodesk CFD, which deals with fluid dynamics, and it'll allow you to do airflow and currents and heat exchanges and whatnot. So one more thing before we run the calculation, we're going to come to the material, stainless steel, and here we're going to make sure that thermal properties are turned on. So here we can see the specific heat and the thermal conduction coefficient. So here we go, and we can also set a reference temperature of room temperature, that is to say 298. Okay, so we're going to run the heat study, thermal study, and it shouldn't take too long. But in case it does, I have one that I've pre-calculated earlier. Here we go. So what it's calculating at the moment will be the heat distribution given the scenario of a fixed temperature at one end and a convection coefficient at others. So what we see here is a nice distribution of the heat flux. So this is in milliwatts per millimeter squared. We can see a heat flux quite a bit is exiting early on. And you might have seen this lots of times in titanium exhaust. You'll see a nice bluing of the pipes near where the exhaust is coming out, that's because most of the heat is coming out at that region, and you get discoloration. Some people love it. Now, what would be a nice trick? Oh, we can also see the actual temperature itself. What might be a nice trick, though, from a mechanical engineering point of view, is what load is going to be imparted on this structure due to the expansion of the metal. So let's have a look at how we can calculate that. It's a bit of a trick. We'll come along and we'll do a new study. It's going to be a linear static study. And we're going to input, as we normally would, we'd put in our constraints. So just for this exercise, we're going to fix it there and there. And rather than giving it a load in terms of forces, we're going to do a very special load. We're going to say a load from an output. So what this means is we can get the output of one study, whether it's another linear static study or a heat study, and use that as an input for this one. So here I'll come along to the thermal, come to the results file, and say OK. Now, because we're inputting a temperature, what that'll do is calculate the thermal expansion according to this coefficient here. So let's go ahead and, oh, that's thermal conductivity, thermal expansion, somewhere around. So we'll say OK, and then we'll remesh and run the study. There we go. This mesh could surely use more refinement, but we're going to continue anyway. So what it's doing at the moment is grabbing the output of the thermal study and inputting it into the linear static study. And here we can see the subsequent stress as a result. Now we can say, and rightfully worry, that we're getting significant deflection in that direction because it's expanding. And we can see also, oops, go to view and orthographic. Here we can see a significant von Mises stress in that little lip where the fastener is coming in. So it might be worthwhile to have a fastener that allows for some thermal expansion. And when designing engines, that's common practice. So that's those are the studies that I want to show you. And I'm going to pass you on back to Simon. So I hope you enjoyed. And if you have any questions, I'd be happy to answer at the end.
Thank you, Frankie. And yes, if anyone has any questions for Frankie, use the questions box. I'm sure Frankie's excitement has generated quite a few questions. He may have answered some of the questions whilst presenting, but it's a huge area. And Frankie, I actually have a couple of questions for you, if you don't mind, before I talk about how great the blogs are. But how do you, in your experience, how do you know what's the best type of analysis to do? And more importantly, when you get the results, how do you know what that means, and how do you know what to do as a designer, as a mechanical engineer?
If you need to verify if the results are okay, there are a couple of strategies. So in FEA, what you can get is, all the time actually, singularities. They're called hotspots alternatively, where you get areas of intense concentration of stress. Now, in real life, it might be a real stress concentrator. That might be like, say, a corner of a design, in which case you'd see a local plastic deformation, in which case the stress would redistribute itself anywhere. Alternatively, it might be an aberration in the calculator, in which case you might choose to probe near the node, which is offending you, and take an average of the stresses in that local area. Now, as for knowing what works and what study to do, that depends a bit on experience. So say, for example, with the pole was a very intuitive understanding of buckling. We've all seen buckling happen. You know, we've all seen poles buckle. And so it's understandable. But say if you're working on a structure that's thin, say for example you're working on the accelerator pedal for a car, you might want to do the study, you know, the nonlinear static study, just to make sure that it works. But then you might follow it up with a buckling calculation, just as a matter of routine, just to make sure that it's not going to fail in another mode that you didn't consider. Sometimes a mode of failure can come out of left field. So you might have, say, a frame on the back of a truck, And you calculate the typical load, you calculate the von Mises stress in linear static, and everything is a-okay. But you're getting premature failure, and it might be a result of two things. You might get vibration from the truck motor, which is inducing vibration in the frame, which is causing a fatigue, happens to coincide with the natural frequency of that structure. Or alternatively, you might have stiffening of the welds, in which case you get a stress concentrator at the welds, and this is very, very common for welded structures. Welded structures have a whole lot of challenges when it comes to simulating them. You've got porosity in the weld, you've got increase in stiffness, you've got changing material properties. And so lots of it comes down to experiences, rules of thumb, and just being diligent with how you interpret the results. At the end of the day, it's a calculator, and it'll be silly in, silly out.
There's a better way of saying that, I think, but we won't do that publicly. And the other question, Frankie, mesh controls. So obviously we said about refining the mesh and making it a smaller mesh. Presumably then a smaller mesh is going to be more accurate, but I guess take longer to solve, right?
Pass me the screen. I'll show you something beautiful.
How do I do that? Pass you the screen. Good question. There we go. Make presenter. Yes.
Excellent. So of the many joys in life, one of the best is a really, really good mesh, and I'll show you the mesh controls that you can do. So there do exist mesh controls in Inventor's native FEA, but not to the extent that you can do it in Nastran. So I'll show you what that looks like very quickly. For this calculation, I used a very coarse mesh because nonlinear studies with a very fine mesh are diabolical. But here I'll come along and I'll introduce a mesh control to this face here. Now I might say, okay, instead of using the global mesh size of 0.75, I might say 0.2 mil, very, very small. Now, it's not the end of the day. I might say generate mesh, and I'll notice something. I'll say, oh yes, Frankie, that mesh is wonderful. In fact, that might even be acceptable. But wouldn't it be nicer if the growth rate of these elements was gradual? What you want in Nastran is a nice gradual transition between everything, and sharp changes in the mesh can lead to singularities in the calculations. So we'll come to mesh settings, come to the settings here, and here we'll do, we'll change the growth rate of elements. So by default, it's 50%, which means that the elements can get 50% larger each time. But this time, I'm just going to say 10%. I'm also going to allow it to project mid-side nodes, which will allow it to conform to curved surfaces a little bit better. So here we'll say, okay, generate mesh. And there, oh, can you feel it, friends? It's amazing. Very, very nice quality mesh. So this is one of the many skills. FEA, in my opinion, is unique amongst the training in that you can spend your entire career honing your FEA skills. What works, what doesn't work, what's a good rule of thumb, what's what's standard procedure. All changes from company to company and engineer to engineer. One of the ones I will impart to you today, if you're looking for to ensure that your results are have fidelity, there's a good rule called the rule of three, which involves using 3 different mesh refinements when doing a calculation. So you might put a load on the lever, calculate your stress, and then you'll refine the mesh a bit, and then recalculate, and then refine it once more and recalculate. And if you see that the results are asymptotically approaching a static value, then you can say, okay, yes, this mesh is converging, and the results can be trusted. Not all the time, but as a good rule of thumb. So yeah,
but I guess Frankie, I guess the smaller the mesh, the longer it's going to take to calculate. I get one of the questions that's come in. Yes. One of the questions that's come in from Charles is whether you can send the solving to network distributed computers, or whether it's just on that single computer.
As far as I know, for now, it's just on the simple computer, but I will give you a silver lining. If you come over here to parameters at the bottom of your study, you can edit it, and here you can edit all the solver parameters that Nastran uses. Now, one of them in here will be the number of cores that are used in calculations. Now, let me see. Yep. Wait, where is it? Transient response, yada, 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 blah, 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 blah. I think it's here. File management. There we go. N processes. So this is the number of cores that will be used in the calculation. So if you've got a very diabolical problem, you might bump that up to 8 cores. Well, maybe I've got 8 cores, so I might say 6 cores. And so when it does the calculation, it will, where it can, use distributed programming, distributed problems.
And there is also another, thank you, hopefully that answers your question, Charles. There was another question from Dan, which was whether the Nastran assembly FEA works in the same way as the Inventor FEA. So should you, if you need to do the same sort of study, is it better to reuse it from what you've done in Inventor FEA in Nastran, or start from scratch in Nastran?
Honestly, I'd start from scratch, and the reason for that is because Inventor's FEA has very simple relationships when it comes to contact surfaces. So I'll very, very quickly open up a quick assembly. Let's go ahead and make. I'll grab actually possibilities, training, and Nastran, and let's go to a simple assembly. So say, for example, here we've got a simple assembly. We introduce a contact surface between 2 parts. So I'm just going to assign them. Here we go. And we'll say contacts. We can do it manually or automatically. I'm just going to demonstrate a manual introduction. So we'll say a contact surface between that and that. Now, how do these surfaces interact? Here in Inventor's native FEA, you can do the same. You can say it's separation, or it's bonded, or it's sliding. But and you can introduce things like stiffness and friction, which you can input here. But Nastran lets you put in advanced options. So, friction stiffness for stick, or, the shear stress, tensile stress for weld damage, radial activation, blah, 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 allowable slip. So you can get into much greater detail with the with Nastran when it comes to contact surfaces. Okay. I hope that answers your question.
Yeah, perfect. And are there any other element types that we can use in Nastran?
Oh, that's a great question to ask. I hope that I had enough time to show you. So very, very often, and this is particularly large for important for pressure vessels, if you have a design, so just give me one moment. So it is learning training, Nastran. Let's go have a look. If you have, here we go. If you have a very, very thin walled design, so it might be like a pressure vessel or a plastic part or a shell, rather than doing a solid study on it, you can do a shell. So what I'm going to do very, very quickly is show you how close a shell study is to a solid study. So here I'll just assign the material mild steel. And you might say, oh, Frankie, why do you keep on using mild steel? That's because I remember all the material properties. So here we go. We'll come to mesh settings, maybe turn on mid-side project, and very quickly generate a mesh. It's looking pretty good. And honestly, for such a small part, I'll probably just do it as a solid. But we'll come along, we'll constrain the bottom. Okay. We'll constrain the bottom there. And here we'll put on a load acting down. It'll be a little load. We'll say negative 15 newtons acting down on that face. There we go. And we'll quickly do a study and calculate just, oh, it might be actually, that's a useful thing to know. The stop button in Nastran is one of the few cancel buttons in Windows that actually works. You have learned a thing today. I'm going to remesh it with a bit of a finer mesh. And here we'll do a very, very quick linear static study using a solid idealization. So basically it's just a solid as per business as usual. So we're just going to quickly note down what stress is induced in it. And we're going to rerun the study, but this time using shell elements. And shells are very, very quick to learn and very, very useful. So quickly we can see here, yeah, we've got small stress, 2.78 megapascals von Mises acting down on that face. So we'll throw out those results. We'll get rid of our solid idealization and create a new idealization. And this one is going to be mild steel, and it'll be a shell. Now, I should have measured it beforehand. Here I can measure the thickness of the wall as 1 millimeter. So we'll say idealizations, choose mild steel, and choose shell elements. And here we can say 1 millimeter and pick all the associated shape, all the associated faces of this shell. There's a bulk way of doing it, but I find satisfaction. Okay, so here we go, and we click OK. And here we can generate a mesh. Now, one of the nice things about shell elements is not only is it much quicker to study, but I'll just quickly edit the shell element. It's possible to describe laminates in this way. So here you can come to laminate, and you can assign plies, and you can create plies and put in angles and actually do, like, say, a carbon fiber layup. Very, very tricky, very, very nice. In fact, I might, we have very little time left. I get to
I'm running out of time.
Okay, no problem. So here we've got, sorry about that. Here we've got the shell. And before I do, I'm going to turn off the model so that we can see just the shell. So there it is. You might say, oh, in which direction is the thickness going? You know, we said that is the shell is going in or out. Very, very important question. So here we can right-click elements and turn on normal display. There's two ways of doing this. There's the color, which shows yellow on the top side of the shell. If you've imported a geometry and one of your elements is upside down, so say for example it looks like oops. All right, you have to turn on CAD bodies. 2 moments. There you go. If it's flipped, you can flip that because we're almost out of time. Yeah, just make sure that yellow is the top side of the shell and thickness goes into the material. So we'll go ahead and we'll assign the load again, just to be sure. And oops, there we go, 15 newtons load. And this time for the constraint, rather than picking the face, we'll pick the edges. Now, people often scoff at shell elements saying, oh, you know, it's the cheap version of solid elements, but they're extremely useful. When you've got a 3.5-hour calculation to do on a body, and you remember my chipmunk voice talking about shell elements, you'll thank me. So here we go, we'll run the calculation, and you'll find that not only is it faster, but the results are much the same. That's safety factor before you freak out. Stress. Come to this shell von Mises stress. And would you look at that? 2.8. Very, very close to our 2.78 result from earlier. So wonderful. Okay. Sorry, I'm taking too much time.
I'll answer your questions. And there's a couple of other questions, and we'll answer them afterwards. But I'm just conscious of time. Grace, I can see you've got an issue. I'll make sure Frankie comes back to you as soon as possible with some errors that she's getting. So really interesting. Thank you, Frankie. Hopefully everyone found it useful. The one for me that's really interesting with my customers is the fact that over time, you know, in the old days, doing analysis was almost you know, it was only for the big boys. It was only for the automotive and the aerospace industry because it's very complex. You needed a supercomputer to run it, and I think the world has sort of changed a bit. So pretty much everyone, small to medium-sized engineering companies, now have access to this technology. So being able to use it, I think, is the key, and that's kind of where we come in, right? So we're here to support our customers, whether it's to train you how to do this sort of stuff, or whether it's to do it with you, which is we often do. But we also have a blog page that's worth looking at, and Francisco has written a number of our blogs around analysis. So please, if you subscribe to our blogs, please have a look on our website for the blogs, because there's some useful information that Frankie's written on this very topic.